Hello, everybody. Welcome to Conditional Statement Practice. So here we're going to be stepping up our work with logic a little bit and getting a little bit more formal and learning a few new words that we're going to use throughout this chapter. So starting out, deduction, I mentioned this in the last video, is the more formalized way of logic, logically thinking. So what it does, it starts with a hypothetical statement, and it uses logical reasoning to reach the conclusion or reach a conclusion. And often what that takes the form of is an if-then statement called a conditional statement. So one of the examples you saw last time of this was if a number is divisible by 6, then it is also divisible by 3 was the way it was phrased before. Here's the one. If it is divisible by 6, then it's divisible by 3. And I actually underline it this way on purpose. This is an example of a conditional statement, and it breaks it into two parts, the hypothesis and the conclusion. For a hypothesis, in logic, they usually use the letter P, because another word instead of hypothesis we can use is premise. And the conclusion is represented by a Q, which I honestly think is just the next letter after P is where that comes from. Not certain on that, but I think so. Anyways, so P is the hypothesis and Q is the conclusion. So there's a first law of logic that says if P is true, then Q is true. So this is how the if-then statement works, is that you start with a hypothetical. So let's say this happens. Well, if that happens, then we also know this. And it uses, again, that logical reasoning to assert that. And sometimes it'll be factual, sometimes it won't. It's our job to figure out if that's true or not. Like if I made the statement, if a number is divisible by 6, then it is also divisible by 5. That would not be a true statement. I can set it up as a conditional, but that doesn't necessarily make it true. Our job is to make conditional statements that are true, or to determine if a conditional statement is true or not. So when I do that, it's called using the law of detachment. If P is true, then Q is true. And that's one of these logical reasonings, or sometimes called the laws of logic, that we're going to be looking at this chapter. Again, just to kind of emphasize, this is the hypothesis, or P, and this is the conclusion, which is often called Q. So we already looked at the first one here and decided last lesson a number being divisible by 6 meant that it was also going to be divisible by 3. So any number that you can divide by 6, well, 6 is the same thing as 3 times 2. So if I can divide it by 6, then I can also divide it by 3, is how we knew that that was true. Go ahead and pause the video real quick and decide if these other 3 statements that involve dividing by 3 and 6 are also all true, or if any of them are false. All right, so as we start looking at these, we have to kind of dissect what has happened here from the original statement to each of these statements. So the second statement, all it does is it flips your P and Q. Instead of saying if a number is divisible by 6, then it's also divisible by 3, it flips it and says if a number is divisible by 3, then it's also divisible by 6. And this is not true, because I can come up with counterexamples all day long. 9 is the first one I think of. 9 can be divided by 3 evenly, but not by 6 evenly. And there are many, many more examples after that. And remember, from the last lesson, all you need is one counterexample to decide if something is false. As soon as you can find one counterexample, you can throw it out. It's false now. So we can decide that is false. Now what happens is we put it back in the original order, P and Q, but they negate both of them. They say both are not divisible. So if a number is not divisible by 6, then it is not divisible by 3. So what I did is I found a number that cannot be divided by 6 evenly, but it can be divided by 3 evenly. So this violates the law of detachment, which is saying that if P is true, then Q is true. Here, I found something where P is true. 15 is not divisible by 6. So P is true that 15 is not divisible by 6, but Q is not true. 15 is not divisible by 3, right? It is divisible by 3, but it's not divisible by 6. So this would not be a true statement. Something that's not divisible by 6 does not mean that it will not be divisible by 3. And then finally, what we did is we reversed the order and we negated both. So in doing this, what we end up with is kind of a weird reflection of the first statement. So we're saying if it's not divisible by 3, then it's not divisible by 6. And this is true for the same reason the first was true. This is saying that if this, then that. So if we can do this thing, then we get that. Therefore, if we don't get this, then we must not have been able to get this. Because if you do get this, then you automatically get that. So if I don't get it, the only way I can not get this is if I didn't originally have this being true. So that's what it's doing, is it's flipping it around and negating it. And it's weird that that's the one that ends up being true. If I just flip it, it's false. If I just negate it, it's false. But if I flip it and negate it, it is true. And turns out, rather than using all these flipping, negating words, we have terms for those. So a conditional statement is what we looked at before. And here's the logical way, or using logic notation. P implies Q is how you would read that. So if P is true, then Q is true. Just like the law of detachment says, P having P be true implies that Q will also be true. Now the converse of that statement, so here's a new word, converse, means that you're flipping it around. Q implies P. And more times than not, that is going to be false. That working from your conclusion back to your premise is not going to work out well. You're going to get a false statement. On the inverse, we introduce a new symbol here. Single squiggle. You've seen me use double squiggles before, which is like approximate, but a single squiggle means not. It's a negation symbol in logic. So if you want to say something is not the case, we would say not minus, squiggle. Not P implies not Q. And that, again, is typically going to be false, where we maintain the order of the premise and conclusion, but we just negate them both. And again, weird enough, this is called a contrapositive, where you flip the order and negate them, and that is typically going to be true. If we don't get the conclusion, then we must not have had the premise, because if we had the premise, we would have gotten the conclusion. See how those two tie together, the conditional and contrapositive, but these others aren't always true. Think back to the example of eating carrots, right? Just because rabbits eat carrots doesn't mean an animal that eats carrots is a rabbit. That just doesn't work out. Same thing here. Something not eating carrots doesn't mean that it's not a rabbit. Like, that's not a rabbit's only qualification. So, not being a rabbit doesn't mean that it doesn't eat carrots. It could be not a rabbit and still eat a carrot, like a horse. Not being a rabbit would mean it could be a horse, but a horse would still eat carrots. See, that's kind of a hard example to work through. But anyways, the converse and inverse aren't always true, but if a conditional is true, the contrapositive will also be true. All right, so let's try using this a little bit to make it a little bit more clear, because that was pretty confusing. So here's a new statement. If an object is a square, that's our premise. The conclusion is it has 4 sides. So that's the P and the Q. Determine from that conditional statement the converse, inverse, and contrapositive. So go ahead and try to pause the video and use what I showed you up here in number 2 to write the converse, inverse, and contrapositive for that conditional statement. All right, so let's check this out. So the converse would be where I flip P and Q, and I state the conclusion first and the premise second. So here it would say, if an object has 4 sides, what used to be our conclusion, then it is a square, which would be our original premise. And once again, that is going to be false. There are plenty of 4-sided objects that are not squares, right? Rectangles, any quadrilateral, right? Any kind of weird 4-sided shape you can come up with, that's not a square. That's not how that works. But it has 4 sides, right? So again, the converse is not true. The inverse, if an object is not a square, then it does not have 4 sides. Again, that is going to be false. Because, for the same reason, if it's not a square, it's saying it can't have 4 sides. Well, here's something that's not a square, and it does have 4 sides. So, all right? And then the contrapositive, if an object does not have 4 sides, then it is not a square. That is okay, because one of the requirements of being a square is that you have 4 sides. So if it doesn't have 4 sides, then it can't be a square. Here's again where you see, if we don't get the conclusion, we couldn't have had the premise, because the premise requires you to end up here. So as soon as we know that we don't have that, then we can assert that we didn't have the premise, or that we don't have the premise. So that's supposed to be a check mark, by the way. All right. Now, using Venn diagrams to do the same thing. It's printed terribly, but what it's saying is on inside the square. But by the way, a Venn diagram is where you have like things like this. Let me actually use that divide by 3, divide by 6 example again. These are all numbers that can be divided by 2. These are all numbers that can be divided by 3. And in the middle are the numbers that can be divided by 6. All right. So over here, we would have numbers like 4, 8, 10, numbers that can be divided by 2, but they're not in the divide by 3 circle because I can't evenly divide those numbers by 3. Over here, I'd have numbers like 9, 15, 21, things like that, things that can be divided by 3, but can't be divided by 2. And in the middle, I'd have numbers like 6, 12, 18, 24, numbers that can be divided by 2 and 3. So Venn diagrams are used to show groupings and how they overlap or interact. Well, sometimes groups are entirely inside of other groups. For example, these are all the people who live in Texas. Here's one here. It's filled with all the different people who live in Texas. Now, some of those people also live in the town called Houston or the city of Houston. Being in Houston means you're still inside of Texas, but not everybody who lives in Texas is inside of Houston. And then, of course, there's us who lives out here. We are neither in Houston nor Texas. We're in Michigan. That's a whole separate little sphere over here. But if there was even a bigger box of people that lived inside of the United States, we would all be inside of that box, right? So Venn diagrams can kind of stack like that. So what we're going to try to do is write these different statements based off that Venn diagram. And I'm going to show you the conditional because I know it's a new thing. It's kind of confusing. So the way this would read is if you live in Houston, Texas, and I included the TX on Houston because there might be other towns called Houston. I didn't want to argue with anybody. If you live in Houston, Texas, then you live in Texas. I know, kind of a dumb statement, right? I'm going to rephrase it. If you live in Houston, then you live in Texas. We're only talking about Houston, Texas. All our Houstons are dead. So that would be the conditional statement. If you are inside of this circle, then you also have to be inside of this square. Right? There's no way to be in Houston, Texas without also being in Texas. So take that conditional. Here's your premise. Here's your conclusion. And try to rewrite that or manipulate it around to write it as the converse, inverse, and contrapositive. Go ahead and pause and try that now. All right, I had to erase and move some stuff around to get it all to fit. So here's our original conditional. If you live in Houston, then you live in Texas. Premise, conclusion. So the converse is simply flipping that order around. If you live in Texas, then you live in Houston. And that's just not true. Right? You could live in Austin. You could live in San Antonio. That's in Texas, right? I don't know. There's lots you could live in the middle of nowhere, Texas. I know that exists. There's loads of places outside of Houston that you could live in that is not, loads of places in Texas you could live in that is not Houston. If you don't live in Houston, then you don't live in Texas. That's basically saying the same thing as the converse. That is also false. That if you don't live in Houston, you could still live in Austin. You could still live in a load of other places that is not Houston, but still be in Texas. So there's all these people out here that prove that that inverse is also false. But again, the contrapositive will be true. If you don't live in Texas, then you don't live in Houston. To be in Houston, you have to be in Texas. To get to Q, you have to have P. In order to live in Texas, if you don't live in Texas at all, you can't possibly live in Houston. So that would also be true. All right, so we've pretty well proven how the conditional and contrapositive are tied together, and it looks like the converse and inverse are kind of tied together, but it seems like they're always opposites. Well, I'm going to show you a couple examples now of when they can be both true. And so we're going to look at that here in just a second. All right, so I wanted to pause and go ahead and just write that out for you so you don't have to sit here and watch me write. But what we've got here is called a biconditional statement. Anytime you see the prefix bi, like bicycle, it means two. So it means that it's going to work both forwards and backwards. So it's a conditional statement and its converse are true. It's considered a biconditional statement. So when that happens, it's called a biconditional statement. Another dead giveaway to this that you'll see sometimes is called an if and only if statement. So it's like saying, here, actually, we'll just jump down and I'll do this example for you. I wear a hat if and only if it's sunny outside. Now, if that just said, I wear a hat if it's sunny outside, that still leaves open the possibility that it could be sunny outside, but I'm not wearing a hat. Maybe I stay in that day. Maybe I sleep the entire afternoon because it's COVID. And so it's sunny out, but I'm not wearing a hat. When it says if and only if, that means that when this happens, that happens. When this happens, that happens. It goes forwards and backwards either way. Both the conditional and the converse are both true. So when you see if and only if, I'll actually even just fill this in for you. This is going to be true. Or it is going to be biconditional. That when it is sunny, I am wearing a hat. When I am wearing a hat, it is sunny. That if and only if is a dead giveaway. And if you do ever take any further logic classes, or maybe even in your higher math courses, you might see this if or IFF. If I forget how to say it. It's been a long time. IFF is a way of shortening if and only if. So if you ever see that, that's what it's referring to. It's stating that this works forwards and backwards. So go ahead and pause and see if you can determine whether or not these other three are biconditional statements or not. All right, so the first one is biconditional. If angle A plus angle B is 180 degrees, then angle A is supplementary to angle B. We can read that backwards and it will still be true. So this is how you check if something is biconditional. If angle A is supplementary to angle B, then angle A plus angle B equals 180 degrees. That is true. Almost every time you have a definition like that, it's going to be biconditional. So like if I am an unmarried man, then I'm a bachelor. If I'm a bachelor, then I'm an unmarried man, right? That works forwards and backwards because it's defining a term, bachelor, right? So those are that's a biconditional. These other two will not be, though. So it works forward. If a number ends in 0, then it's an even number. That is true. Anything that ends in a 0 can be divided by 2. Therefore, it's an even number. But if I read it backwards, if a number is an even number, then it ends in 0. That is not true. The 2, 4, 6, 8, boom. There's 4 counter examples for you. Any even number not ending in a 0 would be a counter example to that. Same here. If it's a Tuesday, then it's a weekday. That is a true statement. The conditional here is true, but it is not biconditional because if I read it, if it is a weekday, then it is a Tuesday. Nah. Monday, Wednesday, Thursday, Friday, those are all weekdays that are not Tuesdays. So these are both conditionals, but not biconditional. All right, our final topic for this lesson is the law of syllogism, which is basically the transitive property, if you've ever heard of that before. If A implies B, and B implies C, then A implies C. So this is just saying, like, if A is true, then B is true. And if B is true, then C is true. We can skip B altogether and just go, if I have A, then I can get to C. I don't need this middle B business. Kind of like the way I brought in the whole idea of dividing by 2 here. I didn't need it because I can just jump from if it ends in 0, it's even. I don't need to say if it's 0, it divides by 2. If it divides by 2, it is even. I can just jump from start to finish. So that's the idea of the law of syllogism. Actually, how about that? I forgot I put that here. If a number ends in 0, then it is divisible by 2. That is A implies B. And here, if a number is divisible by 2, that's the same thing. B implies that it is even. C. So I can rewrite this. I can draw the conclusion. If a number ends in 0, then it is even. Right, see how I'm using A and then jumping straight to C. If this is my A, if a number ends in 0, I skip the whole B part that kind of already springboarded into itself. The first sentence's conclusion, the first statement's conclusion is the second statement's premise. The way it kind of springboards in like that. The last part then is the conclusion, the C. So I can use A to get to C without needing to talk about dividing by 2 because of the law of syllogism. So once again, last time, pause and see if you can use the law of syllogism to rewrite a valid conclusion or to write a valid conclusion for numbers 10, 11, and 12. And some of these, it won't work. And in that case, you'll just write no valid conclusion. So go ahead and pause and try that now. All right. So the first one, number 10 here, says if a dog eats super dog food, then he will be happy. So that is our A, and this is our B. And then it just says Rover is happy. There is no conclusion to be drawn from this. I can't even say that Rover eats super dog food because he could be happy because I took him for a walk. I don't know. This is not following that law of syllogism where one thing implies the next, and then that thing is used to prove a third, allowing you to jump from the first to the third. Right? That is not what's happening here, and so there is no conclusion to be drawn. These other two do have a valid conclusion. So I used one line to underline like A, and then two lines for B, and then a third line for our C. That way you can see how it goes from A to B, B to C, and then I just rewrite it as A to C. Right? So it goes, if you get a good grade in geometry, your parents will be happy. If your parents are happy, then they will buy you a car. So therefore, you can say, if you get a good grade in geometry, your parents will buy you a car. That would be a valid conclusion. And here I would like to remind you that valid and true are not the same, right? This is a patent. The second sentence is probably a false statement for most of you. If your parents are happy, they're going to buy you a car. I bet the first statement's probably true. If you get a good grade in geometry, your parents will be happy. But the final conclusion here, while it is a logical, valid argument, it is not a true statement because it doesn't reflect reality. Try to remember the difference between those things. And then here I threw you a curveball where I put the A actually was in the second sentence. So when you read it, it looks like an angle is a right angle if it has a measure of 90 degrees. And you would expect the second sentence to start with if an angle has a measure of 90 degrees and like springboard in. What I did is I flipped them just to illustrate that you can still draw a conclusion from this as long as you can start with a premise, come to a conclusion, and then use that conclusion somewhere else in the argument to reach a third conclusion. You're allowed to go from the first to the third. The law of syllogism still works here. So if two lines are perpendicular, then they form a 90-degree angle. A to B, B to C allows me to just go A to C. All right, you've got two quizzes to kind of practice in on this. Try to get the highest score you can on those quizzes, and let your teacher know if and when you come up against any kind of confusion, because our next topic, if you don't have a good solid understanding of this stuff, when we get into proofs, it's going to be a real big challenge. So spend some time, work through, and please ask any questions.